Hello, everybody. Welcome to the March 2024 meeting of the Howard Astronomical League. I can see we've got quite a few people online. I'm super excited. We have a decent showing here at the Robinson as well. Hopefully not just because I'm going to hand out free Eclipse glasses, but hey, welcome. Welcome to the meeting. We have a pretty good overall overview of everything tonight. So, and a very interesting set of speakers. All right. So now, if I can figure out how to, it's weird running the meeting and the slideshow at the same time on the same computer and the Zoom call. So apologize that I'm a little just getting it together here. Anyways, wow, I went to the very last slide. Oh, great. And now it's all right. How about if I start at the first slide and my bad, everybody. Sorry, hold on. It's automatically changing slides, so
they're all fine.
Okay, let's try that again. And then okay. So here is our agenda for tonight. I'll have a few announcements. We've got some Star Party news, book of the month. Crystal is here. And then we have two speakers who are going to talk a little bit about the eclipse. And then our featured speakers, we have some folks from NASA who have a really super interesting topic about communication using lasers in space, which sounds like super high-tech, almost science fiction to me. But and then we'll go through our regular process of our regular speakers talking about what's going on in the sky this month in shallow skies and space-based, and then we'll go through a few images, and then hopefully have a little bit of time to kibitz around here if we got enough people in the audience. So okay, so star parties. Our next star party is a members only party on April 6th, which where are we? That's is that next week?
No.
2 weeks. Okay. And then we have the, oh boy, here we go again. And then we have the eclipse on the 8th, and then we have our public star party on the 13th. And we had a really good star party already. Our first star party of the year on the 16th was a really quite a success. We had a lot of members with their telescopes out, and we had a lot of people. I think it was closer to 200 members of the public come out. It was one of those nights where people just kind of, there was never a line at anybody's scope. People just kind of rolled out slowly, and just like throughout the whole 4 hours or whatever that the star party was going on, there just seemed to be people rolling in and rolling out. So it was really fun. And as you can see, we had the inside of the observatory, we had tons of people, and you know, Dale and Hannah at the helm there. Arjun was doing his, and Bob Savoy were doing their regular planet table outside, and had lots of people. So with that, I think I'll move to the next one, which is Crystal. Do you want to?
So hello everybody. Today's book of the month is Rocket Science for the Rest of Us, Cutting Edge Concepts Made Simple by Ben Dillon, published in 2015. So the design and layout of this book is intended to really be eye-catching, a lot of vibrant colors. The diagrams are great. There's a whole assortment of topics. And it's really helpful because the 4 sections that the book goes through, the universe, scientific applications, talking about the scientific theories and concepts are all color-coded at the top. So you can see that this is really a great, kind of a short burst I recommend read. The only thing I would have to say about it is because it's so packed visually, that it can sometimes be a little overwhelming, the amount of information that may be on any one page. So the readability is affected slightly by that, just how much it offers graphically. But it's an interesting book because it really does a quick introduction to a lot of complex topics without needing to like go off course and look up complex terminology or, you know, watch a YouTube video because, you know, you read the book and you're completely lost. So I think it's a great book to introduce you in 10 minutes or less to anything from the rings of Saturn to exploring gravitational lensing, or if you're interested in like the story of pulsars. They're all little quick, 5-10 minute reads at a time. And it's just real fun to read in a short burst and offers a lot of introduction into science, where it's rocket science, but made simple. So I recommend it. It's definitely beginner friendly. I'd say it's probably appropriate for ages 8 and up. So that's your book of the month.
Thanks, Crystal. Okay, next we're going to go into some Eclipse stuff. And we have 2 speakers, Jim Johnson and Jim. You have to be named Jim to talk about the Eclipse.
That's right.
While you're talking, I'm gonna, if the slides go away for a second, it's on some kind of timer slideshow that I have to undo. So I'm gonna fix that if you don't mind, if you can just talk without your slide there for a
I
minute.
don't know if I can. I want to do 2 things to talk about the eclipse. We'll go over some basic things that I've covered over the last 2 years or so, talking about, the eclipse coming up, and then I want to jump forward to it after we get back from the eclipse to the May meeting. I'm going to be doing a presentation on HAL's collective experience during the eclipse and some things to look for there. And so let's talk about that. Eye safety, that was the first thing on my list. Can't stress enough, we didn't have any injuries in HAL last time. Just be very careful. Make sure you have stop filtration for anything that you put in front of your eyes, and Jim will talk about that more in depth. Path of totality, you must be on the path of totality to see the main event, the corona. Closer to the center, the longer your duration of totality. So if you're on the edge, it could be just a fleeting instant to try to get not only on the path, but toward the center. Venues are booking quickly. I'm hearing a lot of things are already booked up. So hopefully you already have arrangements made. Travel. Millions of people will be traveling when I get to my map. I'll talk more about that, but don't assume that you're the only person on the road. There'll be a lot of people moving along the path of totality and toward it, especially in the final hours. Have you seen the slides again, Victor, just briefly?
Sorry.
I don't even know what's next.
Sorry.
I'm just trying to work from memory, and I got nothing. Like almost something.
All right, sorry.
Imaging, probably best left for pros in most cases. The last thing you want to do is encounter a technical issue and get so lost in your equipment that you miss the eclipse. So just be very judicial about that. The weather, you need a clear sky to see the corona, but there are many other observables that you can look for if you're under the cloudy sky. Let's go back to another thing. Observing plan, there'll be other things up in the sky when the moon is in front of the sun. There's other things up there. Be aware of what those things are and see how many of them that you can see. and know what the terrestrial observables are and look for them. We'll talk more about those. There are links to two of the presentations that I've done that can help you with some of these things, especially the observables, more details about the eclipse path and things like that. Next slide, please. So this is about the May meeting after the eclipse. This will be the presentation that I'm going to do. That's going to be HAL collective experience during the eclipse. I did this for the 2017 eclipse. Basically, I put out a call for information, what your experience was. Yeah. Can you go back to that one? I sent the email out about a week and a half ago. A lot of things for you to look for. Just kind of keep these in mind when you get, after you've had the eclipse experience and you write them down. Try to hit as many of these as you can. I'll be asking for any information along these lines that anybody wants to send to me. I'm not going to go through the list here. I want to take the time on that. Next picture.
I'm the worst. Sorry.
So this is the eclipse path. I also asked people to start letting me know where they plan to observe, and I plotted those on the map. You can see down in Texas, around Frederick, I don't know if it's Fredericksburg or Frederick, Texas, San Antonio, San Antonio, and Austin down there. Back up. Sorry. Another group around Dallas, and another bunch around Cleveland. Cleveland happens to be about the closest place that you can get to from DC. But just look at all the big cities along the eastern seaboard that's going to be moving up that way. Would anticipate Washington, Baltimore, Philadelphia, Pittsburgh, places in eastern Ohio, all going to be flocking to that region. So expect that there's going to be some travel there, and then the rest of us are just kind of spread out through the middle of the path. Not too many up at the very end in the northeast. I think that's my last slide.
I believe it is.
Okay. Just one more thing on the May presentation. If you can, I recommend that you be here. It was Phil, you want to talk about how the presentation went last year? Our last eclipse? The one that was,
Yeah, it's kind of hard to remember how it went, but there was a lot of activity, a lot of pictures, a lot of discussion on what people saw and where they went. Yes, kind of come back to the stories. I had a big story myself because I had outrun a thunderstorm for 90 miles to get a clear spot on eclipse morning. So there was all kinds of really cool stories. It was very much fun. There are some of us that don't have a plan where we're going. I don't know. I kind of hesitate to set up a carpool kind of chase because last minute things could change. But what happened to me when I was in Kansas last time, but and ended up in Missouri. But my plan is going to be to about 2 days before to see where the weather is going to be the best. And then I'm going to get up at like 3 o'clock in the morning and start driving, see the eclipse, and turn around and drive home all in one day. So could be a long one, but that's my plan. So I don't have a spot, but I did hear my wife was trying to do a plan to go out to Cleveland and go to the Rock and Roll Museum and everything else afterwards. And the hotel prices in Cleveland were amazingly normal. You know, the hotel rooms were $200 or under, and so then at least I was shocked because everywhere else they're out of sight.
okay, so make some notes, take some pictures. I'll call for them, send them in. Try to be here in the Nature Center if you can for the May meeting. If not, be online, and it'll be a hugely big time.
Hey Jim, can I add something for the safety side? So if you're observing, you have to, if you're looking through optics, make sure you have your white light filter on. A hydrogen alpha telescope's not going to do any good during a total eclipse, but it'll probably give you some really cool views of the chromosphere as you're as it's approaching, going there. But as soon as you see the diamond ring, the big flash, then you could take your white light filter off, because you're gonna wanna do that so you could see everything. You could look up and you'll see prominences. It ought to be beautiful with all the activity, right? But then, as soon as you see the diamond flash on the back end, when things start coming back out, you know, it'll start, it won't be as big a flash, but you'll start to then put the filter back on your optics immediately, because all that solar energy will be coming right down your path. So it's not quite as, you don't have to be quite as fast with the glasses because there's no magnification and things like that, but you gotta get it back on too. Right? You agree with that, Jim?
Yeah.
Okay, thanks. Hey, there was a comment in the chat that the sound wasn't great. Is it better now?
At the moment, it's a little better.
Okay. Let's keep going and see what happens. I think I'm having a USB cable issue. It's just when it rains, it pours. Okay, Jim, as long as you are on, you want to?
Sure. So Jim talked about the totality for those of us who are going to try to head out and get into that nice zone and experience it. But obviously, a lot of people are going to be back here in the Columbia area. And so I thought I would touch upon, for part of the Shallow Sky this month, some of the particulars of the eclipse. The first thing, like Jim Johnson just mentioned, is your eye safety. That is really, really critical. And what I'd suggest, rather than going into the ins and outs of it here, you certainly can go to the URL that I have listed here and get a full rundown from NASA in terms of eclipse safety. And so basically, just like these glasses here, this is what you want to be wearing when you're looking at the sun during the partial phases. And I know HAL has some safety glasses and you're ready to hand them out at the meeting there, but even if you don't, I'm sure that you could potentially reach out to the HAL leadership and we might be able to get you a pair if you're willing to drop by and pick it up. So at any rate, safety first above everything else. You got to make sure that you have your eyes protected and your instruments protected. Next. So from Alpha Ridge, the event is going to start at 2:04 p.m. And when you're looking up, it's going to take a little bite out of the sun at about roughly the 5 o'clock position. The maximum eclipse is going to happen, we'll see here in a second. All right, at 3:21. Okay, and that will leave about 90% of the sun covered. Still, you know, even if it's just 1% left, you still need to wear your glasses. You know, any amount that's beyond totality, you want to have your eye protection in place. And then the final, it'll leave at 4:32 p.m. And at that point, it'll be exiting at about the top of the sun. So those are a couple of events during the partial phase that you can put on your timer and take note of. Next slide. So let's talk about some activities that you can do in our area, even though it's just a deep partial eclipse. The first thing you could do would be to take a picture of it. You need to have a good filter, again, a safe filter on your DSLR camera. And at this point, it might be kind of hard if you're trying to craft one yourself. I don't know how available solar film will be. But if you have some solar film, you can create a filter and then just slide it over the front of your camera and put your camera on a tripod and take some pictures. You know, bracket them probably anywhere from 1/125th of a second up to maybe 1/1000th of a second. You know, depending on what you see is turning out, because you'll be able to view it on the viewfinder afterwards. So that can be a fun activity. Next. You could also get one of these glasses here, cut off so that you have this little mylar part, and put that over your smartphone. And then if you have like some sort of a tripod for your smartphone, you can take pictures of the partial phases by doing something like this. So if you don't have a filter for your main DSLR camera, you could potentially still use your smartphone and see if you can't get some nice partial exposures.
Hey, Jim,
Next.
for the filter on the smartphone, do you have any recommendations as far as like what to set? Like I've got Nightcap as an app, what to set the imaging to try to take the photo at, what setting or anything like that? Any thoughts?
I really wouldn't. What I would suggest is that you get it out there beforehand, on a day before the eclipse, and just try taking pictures of the regular sun.
Okay.
And then figure that you're going to have to drop down from that as the partial phases go forward. So
Okay.
like the biggest photography advice you can give is take lots of pictures and bracket them, different range of exposures.
Gotcha. Thank you. I'll be on travel, so I've got as my phone and a filter with me. So I'll be in Austin. I'm pretty excited about it.
Yeah, I hope we get clear weather down there.
Thanks,
Finally,
Jim.
you could also have some pinhole projection fun. I'm sure everyone has kind of seen this where you can take like a piece of cardboard, tagboard, put a pinhole in it, and then project and see the partial phase. People have done all sorts of neat stuff. Here's somebody with a spoon with holes in it. I've seen pictures taken with a colander. So be creative, use your imagination, and you can maybe get some cool pictures using the pinhole projection method. Next. Of course, if you have a telescope and you are equipped for white light viewing with a safe solar filter, you can do that. But even if you don't, you can use eyepiece projection. And that's suitable even for binoculars as well as your telescope. It's a great way if you're doing projection. You can see here in the image on the right-hand side, you see the image of the sun. Getting a white sheet of paper and projecting the sun onto it is an absolutely great way to share it with a group of people. So if you've got a lot of neighbors or you're doing it at a school or something, this is a great way to show the eclipse. You'll be able to see the sunspots and see the moon moving over it, and it's very safe. The only caveat I would give you is that if you have a finder scope, make sure it's either covered or taken off because you don't want somebody accidentally peeking through that. Next.
And again, that's assuming you have the suitable protection for your scope, right?
No, eyepiece projection is you're just projecting it onto a piece of paper. So you don't have any filter on the scope. You're basically using the eyepiece as a projector. It shoots it out the side or the back of the telescope onto a piece of paper that you're holding.
Wow. So you can point your telescope directly at the sun and it won't damage the optics?
Well, I think you'll see on my next little bullet point, I suggest that you occasionally move it off. But, you can certainly do that for like 5 or 10 minutes, I would think, without any issue. At least with my refractor and my Newtonian, I've been able to do that. One other critical thing, I think we have gotten away from those solar filters that screw onto the end of your eyepiece. That used to be very common back when I was growing up as a kid, and those things break. They crack because of the heat from the sun. So your white light filter should be going over the front of your telescope, not at the back. And then as Victor's just pointing out, you want to take an occasional break to keep the heat from building up. It's a good idea. And I think especially with a Schmidt-Cassegrain design, that's probably even more important. Another thing that you could try doing for the fun of it is if there are sunspots present, try timing the exact moment that the lunar limb creeps up and touches it. If you happen to get similar readings of the sunspot being occulted by other people throughout the country, it could make for an interesting comparison of what time you saw it disappear versus what time they saw it disappear. Okay, next. So here's something. I don't know that we are in deep enough of an eclipse here in our area, but as you start to hit maximum eclipse, the light is becoming dimmer and dimmer. Now, your eyes are gradually adjusting the whole time. It's not sudden, but you could get into a Purkinje effect, which in short, basically, as your sunlight diminishes, the cones in our eyes, which are used for color vision and bright light vision, they get used less and less, and you switch over to the rods in your eye. And the rods are more blue light sensitive. So what can happen is that you may notice that red and green colors lose some of their saturation. Somebody mentioned to me, and this really resonated with me, if you have ever had geraniums, like nice red geraniums with the bright green leaves, and when it's just getting to be dusk, sometimes they look different, they look striking. So, maybe get something red and something green and just kind of take a look at it when you're in the depth of the eclipse and say, is that looking different to me? Am I seeing any sort of a Purkinje effect? Next. Before I go on, I will post this in the chat. That is a great URL where this gentleman goes into the Purkinje effect. So definitely we'll post that in the chat so if people are interested in watching his video. And the next one, same guy brought out a really interesting activity, and I think this one is doable from our area. Basically, shadows normally are always going to be a bit fuzzy on their edges. And that's because the sun is not a point source in our sky, but it's a disk. And so, that's part of the reason why Jupiter, much further away, the sun much smaller, when one of its moons crosses across it, it's a much sharper outline. Compare that to images of a solar eclipse on the Earth. The penumbra, it's a lot fuzzier. It's far less circumscribed. And that's part of the reason, because the sun is not a disk in our sky. However, as the eclipse goes on and you get into this thin crescent, click again. What you could get into is if you take a rod or a stick and you orient it tangential to the crescent, you're actually cutting down on the amount of light that comes from the side. And then if you turn it 90 degrees and make it perpendicular to the crescent, you are going to get more of the not a point in the sky effect. So it's really kind of cool that depending on how you orient the stick when you're close to that 90% level, the shadow may seem sharper than when you rotate it 90 degrees the other way. So just kind of a cool experiment that you can do if you're in the area. I think the next click will bring up, again, the URL. I will post these in the chat. This guy does a great job of showing a potential experiment he's doing for how to document and to take pictures of this. And I think that's the last one. If we click, I think that's it.
That's
Yep.
it. Thank you.
All right, guys.
Really cool. I'm looking forward to doing some of that stuff. So does anybody have any questions? Any eclipse?
Wait, can you go back and click that link that he was talking about, the YouTube link?
I could, but maybe we could do that at the end of the meeting if we have time.
And I'm going to post it in the chat. So if you want to do it, you can.
Okay, great. Anything else? Anybody? All right, if not, then I think we'll move ahead to our featured speaker. Now, there's more than one speaker on, but I wasn't really sure how it was going to pan out, so I have really information for Dave. So he is chief architect of the project, the Exploration and Space Communications Projects Division. He's got a BS and an MS, and from Hopkins and George Washington University, respectively. He has been for a long time at NASA, working his way up the ladder there, and he is currently chief architect, which is a pretty prestigious role. And so, pertinent to our talk tonight, he's the principal investigator for the LCRD program, Laser Communication Network. So without further ado, I would like to turn it over to our speakers. And our speakers include Armen Caroglanian.
Yes.
Did I get that right?
That's right. Good.
and Jimmy Acevedo as well. So thank you guys for being with us. I'll let you drive.
Sounds good. So my name is Jimmy Acevedo. I'll be kind of moderating things along here. And if you have questions, please drop them in the chat. I'll try and interleave those along with the rest of the presentation here. Actually, no, since I'm also on a single screen, I'll have to get to those towards the end. But maybe I'll pause occasionally for questions here. And sorry for springing that extra couple of speakers on you there. Mr. Sanchez did his best, and I did not respond in a timely fashion. So that's why we have one bio here. But we're going to improvise. We're going to be a little bit flexible tonight. We're going to cover a couple of different topics. We're going to start with a high-level view about laser communications and all the exciting work we're doing with that. We're going to do a divert, and as we talk a little bit about some of the ground-based infrastructure, I'm going to put Armen on the spot and talk about his home ground station that he built in his backyard. And then we're going to see a couple of pictures and see some of the videos and get some of the statistics about a mission called Illumity, which has been mounted on the International Space Station. And then we'll have time for some questions at the end here. So before I put Armen on the spot, just to tell us a little bit more about his background and his role, I want to ask Dave, can you just give us a little bit of, give us 30 seconds or so, what does a day in the life of Dave Israel look like? I understand it's very full of meetings, but what does the role as the chief architect involve? And I think you're still muted, Dave. And maybe hardware muted as well. While Dave's troubleshooting the audio, I guess, Armen, could you, I know you're one of our optics gurus, but can you give us more background about what your roles and responsibilities are and what your day-to-day looks like, Armen?
Okay. Greetings there. I've worked with Dave Israel there for many years. It's hard to believe it's coming up on 40 years. I've been working here at Goddard. I graduated from University of Maryland many years ago as a RF engineer, but I've always been an amateur astronomer too. So building telescopes, and also when LaserCom came on here in the last 15 years, I just had to get involved in it, which I've been glad to do that. I see Dave just came back up, so turn back to Dave.
Yeah.
And then,
okay. We're picking you up again. All right, Dave, back over to you. So what does if you look over your shoulder, if we're shadowing you on an average day, what does that look like?
So my job is it's really to be taking a look at the combination of technologies and future needs and what we currently have today, and sort of plan sort of the framework and what is the plan for our future communications and navigation system. So there's something we're working on now called the LunaNet, which is the infrastructure to be supporting the lunar exploration. And so that's where optical communications fits in. And just a quick couple notes just to hand it off to Armen. So I started about 35 years ago, and Armen was my very first office mate. And he was the antenna specialist. I was coming in doing receivers, but I remember, right there, the first time he was talking about his telescope that he had, and we did like a field trip over to his house and saw his whole big optical telescope, and he had a big truck so we could haul his telescope around. And then some years later, when we started getting into optical communications, then Armen was in the right place at the right time where he could merge his communications interests and his optical hobby together. So with that, I'll hand it over to Armen.
And you still haven't let him leave the office, I see. So
right. So. Yeah, Jimmy, I don't know the slides. I don't know if Dave's going to show some slides, and then maybe I'll.
I was going to pop those up here and get to it. So I guess let's come back to that same question for you when we start talking about ground stations. For now, I'll veer briefly over into some of these the talking points. If I can screen share without.
And while you're getting set up there, Armen, maybe we can talk more offline. I'm an antenna guy too.
Oh, very good. Okay.
All right. Hopefully those are coming through. Please holler if not. So again, as you can see, we're talking to you from the Space Communications and Navigation Program Office. The specific division at Goddard is called Code 450 inside Goddard here, but the Exploration and Space Communications Projects Division over here who executes on that at SCAN. So we've been doing radio for decades since the era of Apollo. We are still going to be using radio for decades after this. It's not going anywhere, but as you can imagine, more and more private entities, other governments are, and just within our own government are trying to compete for those, precious pieces of the spectrum that are physically advantageous for communication. So it's getting more noisy, it's getting more cluttered, and we're starting to run into some hard physical limits as far as how much data we can pack into any given transmission of light here. So we need higher bandwidth solutions. We're already starting to need to throttle in some places. The data we're pulling down from spacecraft, we're already pulling 35 to 45 terabytes of data per day through our radio frequency networks, and that need is just going to continue growing. And just a secret here, the radio beams aren't actually green or red, and the laser beams aren't actually red over here, but I hope you'll forgive the artistic license we took when designing the animations to talk to the general public. And there are a couple other things here today that I think astronomers and folks who are a little more in the know may see as their artistic license. So forgive us in advance for that along the way. But all this brings us to laser communications. So we're using infrared light. This is in the 1550 nanometer wavelength. Invisible to the human eye, starting out at usually 10 centimeter telescopes. There's, of course, some beam spread out. We'll talk more about that later on. But a little bit of a roadmap, because everyone loves a roadmap over here. And Armen and Dave, please jump in at any point here. I'm going to kind of run through my pieces, but I would love for you to embellish and embroider, since you know way more about this than I do. I'm just sort of giving the core backbone. But we started in 2013 with LLCD. We hitched a ride on a mission that was designed to actually crash into the moon to study the plume of dust we were going to kick up called LADEE, L-A-D-E-E. But LLCD gave us 622 megabits per second back, which over 240,000 kilometers is not bad at all. In 2019, we launched LCRD, the Laser Communications Relay Demonstration, which we're going to talk a lot more about tonight. Still operational, hitching a ride on a space. I keep meaning to say Air Force, but now a Space Force bird called STP-SAT-6 that is still out in geosynchronous orbit, 22,300-ish miles away. And that'll be talking to Illumiti in a second. Another active terminal of laser communications is DSOC, the Deep Space Optical Communications. That's on Psyche. Is that right, Dave?
That's
Yes,
correct.
that's right. Psyche. Yep.
Yeah, so heading out to Psyche, heading out to survey one of those metallic asteroids and continually setting new transmission distance records. I think the last one was over 12 million miles, but I realize my notes may be a little bit out of date there.
And Jimmy, what's interesting about the DSOC is it uses the HAL 200-inch telescope as the receive side. So that would have never been thought of back when it was built.
I've never heard that bit. That's really exciting. Yeah, what a like.
Yeah,
I love when we're able to repurpose old stuff for newer things and
right.
Delightful. And I skipped over T-Bird. T-Bird's one of our smaller siblings or cousins. I'm not sure what the exact genealogy is here, but that's a 3U CubeSat, also in low Earth orbit here, like Illumiti is. And I'll talk about that in a second. But T-Bird, LCRD and Illumiti are using a very conservative 1.2 gigabits per second encoded. I think it's 2.55 gigabits per second raw. Please correct me if I'm wrong about that. But T-Bird is really opening up the throttle and pushing the limits there. We're able to get over 200 gigabits per second from low Earth orbit. I think they pulled 4.8 terabytes in about 5 minutes on a recent pass back in May of last year. So just sort of showing how, where the future of this could potentially go, showing that increased capacity. The main reason we're here to talk to you tonight, though, is about Illumiti and its confluence with LCRD. This is a real jawbreaker of an initialism. It's got two other initialisms in it, but basically it is a laser modem, a laser terminal that is bolted to the outside of this International Space Station. You'll see some pictures and some video from that later on, talking to LCRD and via LCRD back down to the ground, so showing that end-to-end relay capability here. We're also going to have building a laser terminal I'm going to use optical communications and laser communications kind of interchangeably tonight. I figure you all are fluent in that, but in case that's throwing anyone off, that's why. So last one, O2O, the optical to Orion on the Orion capsule that's going to be taking astronauts back on a ride around the moon. We have a laser terminal there that'll be able to give us that high definition laser relay link back here to Earth. Any other bits that I left on the table with that roadmap before I move on, Dave or Armen?
I think you're fine. You good?
Sounds great.
Just
All right, so why are we doing this? Like I mentioned, the
Quick
RF
question.
spectrum is getting more and more crowded. Just because of the physics, because of the higher intensity and the shorter wavelength of the infrared energy we're using, we're able to get 10 to 100 times on average greater bandwidth compared to the comparable radio frequency systems.
Hey, Jimmy,
That's the biggest thing at the end of the day. Go ahead.
quick question from here, from the Robinson.
Mhm.
I think you said it, but I'm not sure I heard it right. Did you say you're not just communicating from a satellite to the ground, but you're communicating from one satellite to another satellite?
Yes, and in two different orbital patterns, which is extra wild and makes the navigation engineers even more irritated at us, because Illumity is on space station in low Earth orbit, going around the Earth every 90 minutes, moving at 17,500 miles per hour in the Earth frame. Talking to something in a geosynchronous orbit, or I always get geosynchronous and geostationary confused. I believe we are geostationary since we're not on the equator, but you all know better than I probably. Regardless, so we have something that's doing this, talking to something that's doing this, which makes the pointing and precision extra important.
Wow.
Did I kind of answer your question?
Yes, absolutely. That's crazy.
It is, and it gets even better as Dave and Armen will tell you in a minute here. So we need that 2-axis gimbal. This is Illumity, by the way. We need that 2-axis gimbal. All the scopes on both LCOD and Illumity have that ability to do a pretty high degree of precision with their pointing here. And at the end of the day, it's all about the higher data rate. However, in addition to that, there are a number of other benefits here. So the laser terminals are approximately 25% of the mass of those comparable RF systems. And when you're flying stuff to space on rockets, every gram you can cut down saves you dollars. They also take up less, but they're just less bulky, and the power requirements are a lot lower. You're not blasting the signal radially out, even with relatively precise, relatively focused, antenna arrays. You're still, quote unquote, wasting a lot of energy as it's sent in a pretty broad cone. The collimated fine laser beams they use, I think it's about, I don't remember the relative power intensities. I think it's about 10% of the power, but I'd be interested to if you.
Oh, let's see.
Had another question from the Robinson. I forgot to ask you at the beginning. Are you okay with questions in the middle, or do you want us to wait to the end?
That works fine for me. I think it's.
I'd rather have them in the middle, and then it kind of guides the conversation. So when you think of them, then go ahead.
Right.
Yeah, I have a basic question. You're using laser infrared light, so to speak. Is it affected by clouds, and if so, how much?
Yeah, that's the biggest problem. Yeah.
But what's interesting is it can go through like the high cirrus clouds. So it's, but yeah, thin clouds, okay, but yeah, full clouds, no.
And one of the main purposes of one of the objectives that LCRD has been doing for the first couple of years while it's waited for its cousin Illumity to come up to orbit has been characterizing all the different kinds of challenges and distortions, whether it's heat haze or dust in the upper atmosphere, or those. I think the high cirrus clouds are actual ice crystals as opposed to liquid water droplets, and how much of the one we can do a certain amount of extrapolating from models or just our general understanding of chemistry and physics, but there's nothing quite like a good empirical test here. So we've been characterizing exactly what does and doesn't disrupt the signal. But at the end of the day, NASA, despite what some people think, does not have weather control capacity, and so we are going to have to work around those clouds. And the other way around it is, go ahead, Dave.
I was just you were sort of getting into it though, that one of the main purposes of our LCRD experiment is to get this experience of learning how to deal with the atmospheric effects and cloud effects. We've had decades of experience to figure out how much rain margin you need and how to make RF links work with high availability, and now we're going through the experience of the optical or laser comm and trying to figure out how many ground stations do you need to make sure that you have at least one that you can communicate with, for example.
Yeah, and this flexibility note here on the right, slewing a 10 centimeter telescope that can't weigh more than a few kilograms around, just changing a few angles of degree to transmit to it. Okay, clouds are blocking the New Mexico station. Let's look over at the Virginia, over at the Maryland station, or over to the Hawaii station. Is a totally different order of magnitude as far as the mechanical needs compared to moving one of our 5 meter dishes or an 18 meter dish around that takes rather more power and with it the maintenance, and it's just faster to be able to move those along. So many different benefits. We have this wonderful little acronym called SWAP, size, weight, and power that we've already mentioned here. We've mentioned the flexibility inherent of having more space-based and ground-based assets. And then the other,
before we move on from this slide, I was curious about the longevity of the laser. I mean, we have missions with X-band that have been up there and transmitting for tens of thousands of hours. How do we find the laser over time? Is it stable and degrading, or do we have any data on that yet?
I have no answer. I have to look at David.
So far, LCRD's been on orbit now, launched in December 21. So it's going on a little over 2 years. But then and we've seen no degradation or concerns with the laser. We have experience with LiDAR missions that have lasted a long time. So we don't when we did our calculations for lifetime for the mission, the system is designed to I think we said eight years that we expect to be able to survive. When doing that analysis, the laser was not. It was actually some of the onboard electronics were the things that we thought would fail first, and not the lasers themselves.
All right, thanks.
It's a great question. That's actually the first time I've heard that one. So thank you so much. Last talking point here before I jump off is security. You can imagine, like we were talking before about the beam pattern or the cone of an RF beacon from lunar orbit would be about the size of maybe North America by the time it reaches the Earth, whereas a 10 centimeter beam from the moon is on the order of single digit kilometers, maybe 5 or 6 kilometers. So it is just at the physical layer alone, massively harder to intercept to communication, which is interesting to NASA and especially interesting to some of the spookier sides of governments when it comes to it. But just another one of the many benefits of laser comms. But those clouds are a challenge.
And just real quick on the beam width is also there's it's not necessarily like a security kind of concern, but it's just interference and mutual interference. When things are in the beam, then they can interfere with your signals, and so there's that benefit. But then there's also even if we had multiple systems flying, because the beams were so narrow, we could have two systems at the moon, both at the same wavelength, pointing to the Earth. And because the beam widths are so small, they could both be at the moon and be pointing to two different places in North America, and they wouldn't interfere with each other or overlap with each other. Whereas we couldn't do that with our RF systems at the same frequency.
Yeah, if any ham radios in the crowd, you want to try and do that with 2 radio transmitters, let us know how that goes. All right, so once again, this is going to bring us back to, we're going to focus mostly on Illumity and LCRD, like someone had mentioned here. Yes, we're talking from low Earth orbit here with those definitely not pinkish reddish Star Wars laser beams here. Talking to LCRD out in GEO, back down to our ground stations. You'll see in just a second here where on ISS this has been installed, but in November of last year, we took a ride on a Falcon rocket, and a day or two later, we're bolted on the outside of ISS. And again, this is a full end-to-end laser relay simulating a client and our relay server passing things along, whether we're trying to get on the other side of a moon or a planetoid or something, or trying to just bridge some longer distances out. We're trying to prove and build out this the next generation of NASA space-based data infrastructure over here. So This is where we are. We are stuck on the outside of the, or we are carefully bolted and affixed to the outside of the Japanese expeditionary module over here. It took 2 different rides on the robot arms. We got both the Canadarm, unpacked us from the Dragon trunk, then handed it around to, I forget the name of the Japanese robot arm, which then it connected over there and then ultimately plugged on into place. These are some images of Illumity from on the ground here, about the size of a refrigerator, I think 74 inches long and about 36 inches wide, but I realize I suddenly don't know. Armen, Dave, can you call out some other interesting things here? This is the unshielded, this is showing the optics module all buttoned up for launch, but once that's spun around here, this is what the outside of the bandpass filters are, I think. Is that right?
Yeah, and I can't spot it on the picture, but this group would be interested to know that we have our own separate star tracker co-located to kind of help with the positioning and things. One of the issues on the space station is it's large and somewhat kind of flexible and things in a way. And with the narrow beams that we have, having that co-located star tracker helps with the pointing accuracy that we need. And so you see that the optical module, the telescope, is there on the outside. And you, in that picture in the middle, you can see the inside. That's where there's the modem and that it looks like there's more stuff on the inside than there really is when you look at a block diagram. There's a modem, there's controller electronics that take care of the pointing and acquisition algorithms and things for the telescope. Then the modem itself, and then essentially there's just connections to an Ethernet LAN that is on board the space station. So go ahead.
Are you so the space station wobbles? I mean,
well, I don't know if that's probably not the technical master term for it, but it's not necessarily like 100% sort of rigid
Stable,
body as the solar panels are moving and things like that.
oh,
Then the position. So you couldn't just take the calculation of where the telescope is mounted and know exactly precisely the location of the optical module without having something to make sure to correct for any of that variation.
Yeah, thank you.
Yeah, anyone who's built the Lego version of the ISS knows that in the same way that there's not a full rigidity in that static system, especially I think when they do, I think it's every couple of weeks, a couple burns to boost their orbit, because they're still running into, very, 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 very low density, but still there, atomic oxygen and nitrogen from the atmosphere. It just, slows the orbit down just a little bit, enough to start dipping down. So those burns, I think you'll notice a little bit of flexure, especially out at the ends of the solar trusses.
Cool, thanks.
Mm-hmm. This is in the thermal vacuum chamber down at Houston. Is that right, Dave? I actually don't recognize that one.
I don't know, but I don't think it was ever shipped to Houston. So, but maybe I don't know where that is. Yeah,
we put it in a vacuum chamber. We tested it before we launched it. But, you'll see a couple more photos in a sec here. So we've mostly covered this here, but I wanted to show. Oh, I'm still on VPN. I hope my connection's coming through smoothly and that I'm not lagging.
Yeah.
But, okay, great. So like we said, we've been transmitting at 1.2 gigabits per second here, having Illumity talking to LCRD, to the 2 primary ground stations, which we'll talk. Go ahead.
If I can jump in, I guess I just wanted to point out that all these links are actually bi-directional at different data rates. So we can transmit and receive at the 1.2 gigabits per second with LCRD. Though for the space station terminal, space station can send its data from the space station, which we call the return link, at the 1.2 gigabits maximum rate. But the forward link, the speed that we send the data to the station is 155 megabits, which currently the maximum rate that they get is 25 megabits. So even that is a improvement. And those previous systems that were discussed, they also have higher, high data rates associated with those downlink rates that were discussed earlier.
And when you say it's bidirectional, you can be having one of these modules on LCRD can be having a two-way conversation with Table Mountain, while the other module is having a two-way conversation with Hawaii or with Illumity or something at the same time.
That's right. The way, the LCRD payload is set up to be specifically so there's an onboard switch between these two telescopes that are showing that allows you to connect the data between one telescope to the other telescope. But there's also an RF link available, so data could go from one of the telescopes to an RF link back to Earth also.
Gotcha. In case we're cloudy over the entire Western Hemisphere, perhaps.
That's right.
And you mentioned a star camera earlier. I think this is the Starfinder on LCRD. Yeah. I don't know if that's ours. Yeah.
Could you please explain in the simplest terms possible how you attach data to this beam? Is it a certain number of the code of pulses or modulation or what?
Yeah. For the high data rates, we use differential phase shift keying. So it's essentially and this is you can just think of light as a wave, and you just basically invert the polarity, invert the signal with the bit transition, and then if there's an inversion, then you know that like a 1 was sent, as a quick way to think of it. We also do something where it's more thinking of the light as a particle, where we do pulse position modulation, where we actually you split up a period of time into like a multiple of a factor of 2 pieces, and you send a pulse of photons in that spot of time to send multiple bits of information. And actually last week, Jimmy helped out. We did a pi position modulation for Pi Day. There's a short, like 1 minute video that we just posted online last week that explains that pulse position modulation concept.
It's deeply technical. I'll drop the link in the chat when I stop screen sharing in a minute.
Okay.
Before I move on, Armen, can you talk a little bit more about the ground station positioning? What went into figuring out? Oops, let me actually start the animation again. What went into picking, Table Mountain and Haleakala, and then how does that compare to the GGAO or the ground stations that are just outside our facility here in Greenbelt?
Okay, yeah, the Table Mountain facility is actually run by Jet Propulsion Laboratory, JPL, and they have a mountain out there, I guess. So there has pretty good clear sky conditions. And then the Haleakala was picked also for it's up at 10,000 feet. There's an observatory there, and has good, again, the cloud statistics are and also the observing for the view angles to the LCRD, and gives you also some site diversity too between the various locations. Another site we have for the lunar laser comm system is at White Sands, which is White Sands, New Mexico, outside of Las Cruces. And we have an RF ground station there, and it also has some good cloud statistics, which are decorrelated from the ones at Table Mountain. So that's good too, to find a link. And the Goddard one is not so much for the clear skies around here, but it's more just convenient for us to do ground station development. So those are our various ground stations.
Yeah, we're amateur astronomers. We know all about the cloud statistics around here.
About the pea soup that we have to
yeah, it's about,
we have another question here in the audience.
Yeah, I had a question. So like, since the laser is coming all the way from like outer space to a certain location on Earth, like how easily could the data be like intercepted?
So that'd be pretty tough, because not only you would have to be able to sort of know exactly where in the sky to look, but you'd have to move yourself to actually get in that, let's call it a 10 kilometer, let's be generous, let's call it a 10 kilometer target. in the same way that if you look at eclipse maps where people have to, pretty hustle to get in the path of totality, you would have to be able to move yourself along the way and get in somehow in front of the beam without being noticed by anyone, at the ground station observatory. And then also get a lock and be pointing exactly along the way and following exactly where the satellite is in the sky. I don't know how to quantify that exactly in terms, but let's just say that I wouldn't want to be the one who got tasked with trying to do that. Maybe Dave or Armen can expand on that a little bit more.
Right. So it's
All right, and also, how much power is like required to run the laser? Is it like power intensive or like?
So actually, the laser on board is what we did from the moon was only a 0.5 watt power laser. It's about the same, like what we did from the moon is the same laser power as like a CD-ROM card would have in your computer. So it's a very low power laser from our ground stations. Where we're trying to go through the atmosphere in that other direction to a much smaller aperture. There we have a 10 watt or 20 watt amplifier for the laser power, but it's very low power coming from space.
Yeah, and I think it's even lower by the time it reaches the terminal, because I think it's down to like, what is it, three-ish watts actually emitted. So basically, we couldn't hurt anything with this, even if we tried and had a lot of time in a Fresnel lens, and whatnot. It's extremely low power.
All right, thank you.
Great questions. All right.
Another quick question. Since lack of clouds seems to be the order of the day with where you put your ground stations, is there any problem with putting a ground station at some of the other great observing places around the world, like Chile, or they probably have the bandwidth to get things back here since all those giant telescopes are going?
Yeah. And so there's been lots of studies over the years about, where are the best places to put ground stations? Like, is it better to have infrastructure and high data connectivity and give up some of the weather statistics, or because like, for example, some of the places that you all are familiar with that are great for astronomers to go, where there's great seeing and you can have your telescope and look, they don't necessarily have high data rate connectivity in and out to them. So there have been lots of studies about that. How many ground stations should you have, and about the correlation of the weather and atmospheric characteristics between locations. So that's really what we're a lot of what we're putting to the test with this, because now instead of going with the models, and we're experiencing it. And so, for example, last year was a really bad year to have a ground station in California. They had the fires. They had blizzard. They've had all sorts of trouble there. So we are actually learning, quite a bit. And in fact, we the conclusion so far is that the most available and reliable part of our system are the parts in space, where we built it for that long-term reliability. It's the dealing with the weather and the issues at the ground station has been where we've lost our availability time more than anything else.
Gotcha. And while you're on the subject of testing, Dave, can you give a quick plug for the experimenters program?
Sure. So we have our share of experiments that we've generated ourselves that we want to do for NASA purposes, but we've also been running experiments for some folks out in industry that had a terminal that they wanted to see it work, or people wanted to collect other sorts of data. So we've had this experimenters program where there's a process for people to contact us, and we try to accommodate as many experiments as we can while we're up on orbit.
Excellent. And before I move on, this picture here is of LCRD of the whole payload sled here, about the size of a queen bed, if I recall correctly. I don't think I think these are the dummies. I don't think the optical modules are mounted on in this particular shot, but just to give you a sense of the scale of LCD compared to Illumity. All right, so before, in a sec here, we're going to transition back to a smaller homebrew context, as Armen will share a little bit of his journey in building his backyard observatory. I think I've probably stolen my own thunder already and stolen it, but showing some of the reasons for those ground station locations, some of the just, hedging our bets and increasing the chances here. But you can see some of the infrastructure in these animations. I think this one is the Table Mountain one, the smoother, sleeker white fiberglass hull. That's what the one at Greenbelt and Haleakala are, if that's correct. And then the third ground station for Artemis 2, that's the White Sands one, right, Armen?
That's correct, for White Sands.
Okay. So while as we transition briefly away from you talking about laser ground stations, Armen is one of our is a passion. And oh, here we go. These are the shells that I was talking about earlier. So this is the one in Greenbelt over here. Can you just sort of point out a couple of the other major differences in technical differences beyond this one? Or this one has the shell open here, so you can see the telescope with the telescope inside. It'd be the same kind of four barrel hardware. Is that right?
Different. Well, the one in the center there at Greenbelt, we have a 0.7 meter plane wave telescope, and they've built a lot of telescopes for the high-end amateurs and universities. So that's what we have in our Greenbelt facility. And one on the left is the Lunar Laser Com. One has 4 16-inch telescopes for the receive, and then it's like a cluster of 4 6-inch telescopes on transmit up on the top. And that's all in an environmental, we call it football helmet, which is an environmental enclosure to keep the temperature of the optics at stable. And then the back, you have just some antennas there for the track and data relay satellite system. So they're kind of co-located there at White Sands. Then on the right is the OGS-2 up on terminal up on Haleakala on Maui, 10,000 feet. And what's interesting about that one, the telescope, it has an optical window in the dome, so it's environmentally controlled inside, which makes it kind of nice there for the facility. And you can point this like eye around in the sky and to your comm. So that's kind of a nice optical window, but it's very expensive, those, because they have to be optical quality and they have a solar projection film on it. But it is the kind of the ultimate for protection of the telescopes.
And is that for full operations, or is that just like for your course beacon finding, and then once you're sort of sighted in, then you can open the dome, or this can stay closed for
it can stay it can stay closed during all the operations. So it's really nice feature there.
So at this point, Armen, I'm going to hand over to you. I'll just drive along whenever you want me to click through here. But if you can just tell us a little bit more about building your backyard observatory and walk us through that journey.
Okay. Yeah, this is some few slides that Jimmy selected from a presentation I have for building backyard observatory. About the same time I was getting involved with the optical comm ground stations, it was getting hard to move my telescopes around. So I decided, hey, we need to get an observatory, try to build something there. So this is just my house in Montgomery County, and kind of where does one put a observatory? We have a mandatory setback. That's a dashed line from the property line, and then south is to the bottom. So I wanted to get it as far to the north I could, so I could see the south. And you have things you have to miss, like septic systems. Also, that's kind of where the observatory was located. And let me go to next slide. Here's like a groundbreaking of years ago, and I had to get a permit there from the county, so we got that. And the observatory is up on 6 piers that bring it up a few feet off the ground, which helps in the seeing. And this is unlevel; the ground is not level there, so it helps to kind of set it all out. You'll just see in other photos. Okay, next
This
slide.
is the county inspector, I take it?
That's right. He's checking out the holes there. We went down about 2 feet for the thing. Okay, here's like but this has a combination of a couple things. In the center is the pier from Greenbelt, which is similar to the pier we used in White Sands. It's called a spread footing pier. So it gives you great stability because you go down, I think it's like 20,000 pounds of concrete, and you want that stability. So you go below grade and put this foundation down, and then you come up and then you bolt your telescope to the top, and you need that stability for precision pointing. So I kind of took the similar, much smaller scale, but on the left, you see at the backyard observatory went down about 4 feet. It was, and then put down a little pad and use alternating concrete blocks and brought it up. And on the right, you see kind of where the top of the pier is, the concrete. My dad, who helped me out on this project, we're leveling up the pier and put in our anchor bolts for the telescope. And in the back, you also see one of the piers for the building, which goes around the pier. They're isolated, so that's what you need to do. And same here with all the ground stations. The piers are isolated from the building, so there's no vibration transfer. For any questions there?
And like I'm saying, we have pretty cruelly truncated this slideshow here, but I'm sure Armen would be happy to share it with any folks who want to go more into the process or would be interested in emulating that. So we can, if you're interested in that, reach out through Victor. We can maybe have that conversation further.
There's a lot more in the details and the planning, but okay, please. Oh, here's the telescope.
I plan on following up with you. This is awesome.
Yeah, it'd be good. We can maybe share a little presentation there, kind of the saga of building a backyard observatory. It took a lot more time and energy than I thought. And I'm still kind of working on it to finish it, but it's been quite a project. So the telescope I chose to put in here was my Celestron 11, and then you have the walls that are 6 feet up. So what do you do to get look over the wall, kind of down? So this Pier Tech has the kind of neat little thing, elevating pier, so you can sit down and observe, and then you can also, if you want something low elevation object, you can bring up the pier, and it's there's a trade-off there on stability, but it's not too bad. And so that's a trade you take. So that's the elevating pier.
Hey, Armen,
yes,
is that more of a visual elevating pier, or is it accurate enough to maintain polar alignment?
Yeah, well, it will maintain polar alignment. Like visually, I mean, I guess what has been told is if you wanted to do it for photography, like kind of set a height and go back to that same height, because it does vary a little bit. But if you have an object in the telescope and you move it up and down, it basically stays stable. I mean, when you're up at fully extended, though, there's more vibration though when you're down below, but it seems to work out fairly well. It's mostly visual. I do mostly visual observing, so I haven't noticed any problem. Okay. Here's just myself, my full PPE or whatever, and just doing some grinding or whatever. I did a lot of lessons I learned from the Goddard Observatory. They use steel rather than wood for the gantry. So that was 100-pound I-beam that we got up there. And then they also use something to capture the roof. So when the roof rolls off, if a wind came, you wouldn't pull it off the track. So that kind of complicated the setup there, but it did help out. And my dad's learned welding. He's a welder, so he helped me weld all these pieces together. So it's been quite a task. But anyway, that's just some of the details of the building the observatory. Here's in operation there. We're showing the raised platform, and then the building like 10 by 12, and then the roof rolls off to the west. And it turns out when you get up a little higher, the seeing is a little bit better getting off the ground. And I've actually found it in the summer, the mosquitoes have a harder time finding you if you close it up. They got to go up and over to get to you. So that's kind of a fringe benefit. So that's
no, you designed that in from the beginning. That was very clever bioengineering, right?
Yeah, and I was it's just happened to be that way, so it's worked out. But here shows it in the kind of open, going to the west, and the angle of the roof, just kind of closing it up so you kind of look over to the west. I couldn't go to the north; that would have been better. But here we got the kind of showing it, closing up.
Can you do work from there and then take a tax deduction?
Yeah. There's been jokes about setting up a ground station there, but it's just really for fun. Yes, that's the kind of backyard observatory, and this is just some of what you can observe. Everybody, you guys are all amateurs, so you know what you can observe from around here. I do like looking at comets, so it makes it nice. I can go out, and the Celestron 11 has a nice thing called a hibernate mode. so you can put it in hibernate. Then when you come out, the telescope will use GPS to get the time, and then all you have to do is like point at one star, and then you're aligned, and you can go around and do your work. So it saves time there. So you can, like, in daytime, look at objects, and then I guess there's a program too for the Celestrons that they can track satellites. So it's been interesting to see, like, ISS there, and anyway, just fun stuff.
Thanks for
So
that.
that's going to bring us back there, and again, we'd happily follow up with more about that. But if you forget everything else that we've talked about today, hopefully you'll learn a little bit more about some of our NASA's first two-way end-to-end laser relay system. I'll show in just a second here. I'll have some more pictures of Illumity from the unbuttoning, the removal from the Dragon trunk. But kind of thinking as the chief architect today, and less as the PI for LCRD. Excuse me, as the principal investigator for the laser communications relay demonstration. What's next out beyond the roadmap? What are you excited about? Where is the future for this? What, and kind of, Ty, why is this important?
Sure. So one thing that we are right on the verge of doing is starting to do some experiments over the system that you see in the picture, but to demonstrate some networking and network protocols, DTN, delayed disruption tolerant networking protocols to demonstrate data, to and from the space station by laser. So that you should be on the lookout. Hopefully in the April timeframe, we'll have kind of like a press release, just kind of talking about the successes that we've had with this experiment. And then we'll continue. It's not clear how much longer Illumity will be operating and working on from the space station, but LCRD will be continuing for us to do multiple more experiments. And then when the Orion, when the Artemis 2 mission flies to the moon, now scheduled for late 2025. So this will be astronauts not landing on the moon, but it'll be the first time that there's astronauts flying to go around the moon. And there is an optical laser comm system on board that mission that we call O2O, and that's already installed on the Orion capsule down there in Florida at Kennedy Space Center. So when that goes up, when the astronauts are flying around the moon, then you can expect to see this time HD video pictures coming back, and that'll be carried by laser communications system. Very cool.
So I actually hadn't seen these photos before today. I think this is close out and check out on the ground in Florida here. This is the interface, I believe, to space station. I think it's a standardized payload interface that's with where the coolant to the main radiators on ISS plug into. We get our power and our, I think that like Dave mentioned, that 25 megabit per second Ethernet connection.
Yeah, no, there's a gigabit Ethernet connection and a 100 base T Ethernet connection, and the power and coolant. It was actually pretty amazing so we went up in the Dragon, installed in the Dragon capsule. It's in the trunk, they called it. So it was external. It was docked and outside of the space station. And then, as Jimmy described, one robot arm grabs it, takes it out of the trunk, passed it over to another robotic arm that then slid it into place. Oh, perfect. And then it's connected. So there's no spacewalk. Astronauts don't have to go outside to hook anything up or anything like that. It just it's all built so that it goes up there, and the robot arms have these standard connectors, and they hand it off to each other, and then they slide it in and hook it up, and we powered it up and checked it out, and now it's working.
It's a major improvement over the Hubble user experience, as I understand it. Yeah, so this is, I think, the Canadarm connecting to the I forget the H plate over here, and then the FRGF is the This is the secondary, the Japanese arm coming up and taking control over for that final installation, I believe, to the outside of the B module. Or maybe this is the previous payload that was in there. I'm not entirely sure of the order of operations at this point. I just saw this photo for the first time today.
Yeah, I've never seen that photo. That's pretty cool.
Oh, you know what? Maybe this is our berthing dock. Actually, now that you know what? No, I don't. I am completely guessing here, and so I will steer away from that. So this is the and again, this is So this is all happening extremely slowly. So any of the animations we'll show in a second are highly sped up here, but having to deal with just the optical conditions from going into and out of Eclipse once, every 45 minutes as ISS is blasting around the Earth. So you would be nighttime and then daytime and then, and daytime over again. So it was pretty exciting watching that stream here. So I think this is 180 degrees flipped over, but you can see again the Canadarm getting ready to hand off to the Japanese robot module over here. And then this is our first light here. I have muted the sound, but this is again a highly sped up animation of us just doing our first initial checkouts. Power on, testing the pointing mechanisms. The single point of failure on this one was the release mechanism. Is that right?
Yeah. So, yeah, one of the first milestones was like popping the latch to be able to see it. So it was cool. It happened right during a weekday. We were able to be sitting in a meeting and bring up the video in the middle of the meeting and watch and see that moment when there wasn't. It was kind of a small thing to see, but it was a big deal for those of us that knew what it was. And then this video was the checkout and to be able to steer it in all directions. And then you saw that we're pointed towards the camera and could see that the reflection and everything.
Yeah, the first selfie there was a triumphant noise, and I understand. I think is it a reusable I think it's a hot wire embedded in a paraffin seal. So when it's secured for launch to orbit, that paraffin is frozen around the wire, but then they can heat the wire and release itself, but that can actually be reused if they needed to stow it for some. If there were a more violent or jostling maneuver on station, or am I remembering that?
Yeah, I don't think they can reseal it completely without touching it, but that I don't know for sure.
Gotcha.
But I know they could test it on the ground, and then with people involved, then they could seal it up.
That makes sense. But with that, I leave you with this final closing picture of a. Oops! Oh goodness! No, we were going to go right to that video here. I think I'm just going to close out of the screen share lest I do that again. But that concludes the formal end of the presentation. I don't know, based on how much time we have, Victor, if we have some more time for questions, or if we should wrap up and cede the floor. But thank you so much for your attention. Thank you so much for your questions. And please stay tuned as we keep doing more fun things with lasers and the ground stations that make them go.
Cool, thank you. We have time if anybody wants to ask any more questions.
I have a question.
Wayne has his hand up.
Hi, I was wondering what the pointing requirements are for your ground stations. I assume you do some of your communications in daylight, so getting star fields and doing plate solving is going to be difficult.
Yeah, the probably it's down the arc seconds. It's their sub arc second. It's really right on. Especially the turbulence is worse than what our pointing is. It's pretty amazing. So before the pointing, you'll go to like a bright star, IR star, and get that nearby, and then you can go on to the target. So and you can see stars in the day, which is pretty amazing. But that can be done. So it is arc second pointing.
Okay, thanks.
So there's no sneezing allowed near the telescope, I take it?
No, it's the thermals all. Yeah, it's all there. It's got to be right.
So that kind of answered my question. So you can get information from the satellites on the ground during the daytime.
Yeah, you have to have the solar filter right over the telescope, right? And there's a little keep out zone around the sun. They can be pretty close. It can be 5-10 degrees or so. You can get up, but yeah. So the filters is what you need. You can do that.
Resume?
Yeah, what sort of like processing methods being used to interpret the data that's coming in?
You might have to get a little closer.
Yeah, could someone relay that along? Or?
Yeah. what processing methods do you use to like interpret the data that's actively coming in?
So what sort of mechanisms do we need to process the data that's coming through? I think it's mostly modems that are sometimes depressingly similar to the modem, fiber optic modems you might use for terrestrial systems. Is that right?
Yeah.
Is that the question about how we get the data in and out of the yeah. So the interesting thing is that so for the space station, the experiments that we're going to be doing there's a laptop computer that has software on it, and it's connected to an Ethernet LAN on board the space station, similar to like if you had an Ethernet cable, or there's probably one in that building somewhere, where it's connected to that, and it's actually an Ethernet interface that connects to our modem, but then it's inside of our modem box that takes the Ethernet data and connects to the modulator to turn it into the photons, the modulated light that we send then through the link.
Offline, I'll explain to Arjun how BPSK works.
Yeah, that's great. One of the things that I think that's neat is the whole thing about light being both particle and a wave, and one of our modulations is it's very much like a wave thing, and then the other modulation we're counting photons, and you have to think of it more as particles. So it's my background was not at all in lasers or optical and or any of this. So I got some crash courses when we started this this project.
Curious if the powers that be tried to force you down the road of encryption on any of the links, or do you have encryption on the links?
So yeah, there is encryption on a lot of our data streams and the links, and it's so we have it for data from the space station, like our test data is different, but like for the space station data, it's encrypted. You have like astronauts' health data and things like that in there. But certainly in today's era, we do encrypt our command links and things.
And the encryption doesn't add any significant processing. It maybe adds a few milliseconds at either end. Is that right?
The challenge with encryption, depending on the complication of the encryption, is processing power. So that's having the processing on board to do it. The more difficult encryption you can't do necessarily with software, and then you have to have like a hardware encryption device. So it's some mass and power kind of hit that would happen, but it doesn't affect. It generally doesn't affect the data rate itself.
Thanks.
Like replace our internet, like our normal form of internet someday?
So it'll work with it. So when we do this upcoming networking experiment that you'll hear about, and if it goes well, if you see a news story about NASA sending a whole bunch of pictures of cats and dogs over laser beams, and that was me and our project. Okay, so we're trying to find a way to get more public interest. So I think it would be cat and dog pictures as our test pictures. So but it's we'll be using network protocols. There's certain aspects of the terrestrial network protocols that we use here on Earth that don't work so well with the delays of how long it takes to get signals to and from space and some of the other situations. So that's where we have these delay tolerant networking protocols that we use. But it won't replace what we have on Earth, but they're intended to work together. So we're working on a thing that we call LunaNet that would build out the network to include the moon, and then also working on a project called the Solar System Internet. So trying to get everything all networked together.
One of the stories that Dave was telling me around the time the Lumen T was launching is that if you were to look up, if you were to rise as a viewer above the plane of the ecliptic and watch these beams moving over, even over lunar distances, you would see of this, but it would be especially accentuated over the tens of millions of miles for Psyche, or if we start talking to a Martian relay or a Martian orbiter, that instead, the light will still be moving in straight lines because that's what light does, in most circumstances. But the pointing ahead that one will need to do to actually reach the target means that it's going to look more like a garden hose playing along with just that pointing ahead mechanism to actually intercept over those time scales and distance scales, which is just really counterintuitive to thinking about something that's moving at miles per second. So,
Wow, thank you. Are there any other questions? Can we give another round of applause?
And I just add one more thing to pass on is, so I was actually I was fortunate in my job in 1998. I got paid by NASA to provide. I built a system that provided the comlink for the first live webcast of a total solar eclipse, and that's why I got sent to Aruba to see that eclipse in February '98, and then in August of 1999. It was even better than NASA paid me to take my equipment on board a cruise ship in the Black Sea to see the total eclipse in 1999. And I thought I had it made. I would be sent by NASA to go to every place an eclipse was, every year. After that, then the rest of the world caught up, and they didn't need NASA systems to do live webcasts of eclipses anymore. But I guess but the thing is those of you that aren't sure whether it's worth the drive to go see a total solar eclipse, I would say it's 100% worth it, because the difference between like 99.9% and 100% is just huge.
Would you say it's night and day, Dave? Sorry, never mind.
Yeah, no, it's just really dramatic and amazing. I don't think I'm gonna make it to see the total eclipse, but I highly recommend it for anybody that's on the fence.
Thanks
Thanks again for having us. Thanks for letting me fold in Armen as a surprise guest. Appreciate Victor and Phil putting us in touch with each other and hosting us. So have a fantastic evening. We'll all drop off at this point. Take care, folks.
Okay, thank you.
Thank you.
Armen, you guys are welcome to stay if you want. We'll be on for another half an hour. You can, but if you got to go, you got to go. You could see some of our Astro photos.
Thanks.
Okay,
Thank
good.
you guys so much.
Okay,
Thank you. Okay, appreciate it. Okay.
Okay, so let's go ahead. That was really amazing, and let's move on to the rest of our meeting. So, Jim.
All right. So going to other than eclipse stuff, there's still stuff happening out there. Right now, Mercury is about as good as it's going to get for this year for its apparition, its evening apparition. So it will reach greatest elongation, in other words, its greatest apparent distance from the sun on next week, March the 24th. And I know we talked about this at one of the sessions last year. Every January or December, Sky and Telescope puts out this Observer's Almanac. It's like a timetable of the heavens, which actually was done by the Baltimore Astronomical Society, Maryland Academy of Sciences, years ago until Sky and Telescope took it over. But it's a great graphic way of showing you when you've got a good Mercury appearance. And you can see here by the yellow arrow, this particular elongation, Mercury is setting just at the end of twilight. So you've got a fair amount of time, Mercury-wise, where it's going to appear in a sky where it's dark enough. Still use binoculars to pick it up as soon as you can after sunset. But this is your best opportunity, unless you're going to get up in the early morning to catch it this year. You can compare it to the one in like June, early July, and it's setting before twilight is even over. So catch it while you can. If you've never seen Mercury, at least you can say bragging rights, I got to see it.
Yeah, we had a couple of scopes on it at the Star Party last Saturday.
Great.
So, was at least one Dob Somebody had just pushed right to it and found it right, it was very obvious.
Awesome, awesome. All right, next slide. So Comet 12P Pons Brooks, that is still out there, and it's going to continue to improve a little bit for a couple more weeks before we lose it. And actually, here's a picture from Steve Rifkin, who took it with C-Star at the Public Star Party, I think the other night. Yeah, March 16th. So now, granted, it's going to look a lot more impressive with something like a C-Star where it builds up the image. But still, you know, this thing only comes around every, I think, 70 some odd years. So it's kind of like Halley's Comet in that regard. So get out there, maybe try to catch it. You'll notice on the map in Sky and Telescope that the end of this month, the 31st, it is right by the brightest star of Aries. So that if we happen to get a good clear night, that would be a great opportunity to step outside after sunset, let it get a little bit dark, because it's going to probably be about 5th magnitude, hopefully, and just see if you can pick it up and you can say, again, kind of bragging rights, I got to see Comet 12 Pons Brooks.
So that's also low in the west,
Yep.
around dusk.
Yep, all the action's low in the west. And I think that's my last slide, but I will throw one other thing out here. There is, over the next several weeks or months, there is going to be an explosion. And I'm talking about T Corona Borealis, which is normally a 9th magnitude or so star in the constellation Corona Borealis, which lies between Bootes and Hercules. But about every 80 years, this star blows up. And there's a great article in Sky and Telescope explaining it. You can go online and probably research and read more about it. But again, this is going to be a once in your lifetime event. We don't know when. You know, we should probably start a HAL pool in terms of, you know, dates, and whoever gets the closest wins something. But, you know, keep your eyes and ears peeled to the HAL list, hopefully as soon as it erupts, because it's not going to stay at 2nd magnitude very long. It zooms from 9th magnitude up to 2nd magnitude. Won't stay there more than like a day or so. But, you know, stay tuned, because that event is probably going to happen sometime this spring.
Cloudy night.
On a cloudy night is right, Phil.
All right, thank you. That was awesome.
Just a quick addition of what you said, that the Baltimore Astronomical Society used to be responsible for Sky and Telescope. That was our very own Paul Watson that was responsible for putting those together. And we have a copy of one of those original draftings at the observatory on a large piece of paper from 1979, I think was the one we had.
And think about him doing all of that without computers, you know, using a
Yep.
slide rule and just figuring it all out.
Wow. Cool, thanks. Wayne, are you ready?
Sure. Do we have time?
Yeah, sure.
Okay. So I'm going to continue actually talking about our space communications today. So I want to give a update of the Voyager 1 status. So just to remind everybody, Voyager 1 was launched from the Kennedy Space Center in September 1977, just about 47 years ago. So it's been out there for a long time. It conducted flybys of Jupiter in March of 79 and Saturn in November of 80 as part of NASA's Grand Tour concept of missions. The Grand Tour was designed to take advantage of a special alignment of the outer planets, which would allow for spacecraft to slingshot from one planet to the next, which provides a cheap and attainable quick survey of the major bodies of the solar system. Remember, at this time in our history, we had never sent any spacecraft out that far. Well, Pioneer 10 and 11, I guess, but we had just barely done it. So it was really important to be able to do this. These alignments of the outer planets occurs about once every 175 years. So we had to take advantage of it. So Voyager 1 provided close-up images of both Jupiter and Saturn, which greatly enhanced our understanding of their atmospheres, their rings, and their moons. Voyager 1 was also the first spacecraft to photograph the Earth and Moon from a distance. So we're not talking about the Apollo 8 Earthrise photo. We're talking about seeing both the Earth and the Moon as separate objects from a point in space. It was also the spacecraft who took the famous pale blue dot photo of the Earth, which showed literally it was like 1 or 2 pixels from the outer part of our solar system, and it was part of a solar system portrait. It did that in February of 1990. And this was the last image that they took from Voyager 1 because the cameras were taking up so much power they couldn't afford to actually use them anymore. And plus, for a planetary imaging satellite, or spacecraft, there was no more imaging to be done. And finally, it was the first spacecraft to enter interstellar space, which it did in August of 2012. And it's still going. So next slide. And there, that was a picture of the launch. So just as a real quick, so that's a photo from the from JPL of the launch from of Voyager 1. Next. So here's just a couple of representative photos of, you can see Jupiter on the left with its moons Io, and I believe that's either Europa or Callisto, I'm not sure. And then on the right, of course, is Saturn with a couple of its moons. Just want to point out that at the time, this time in history, these were among the best photographs of Jupiter and Saturn that we'd ever had. Next.
And wasn't Carl Sagan like really excited and like involved in showing these to the public?
Yeah, Carl Sagan was at least part of the Voyager team. I think Ed Stone was the program manager, but Carl Sagan was part of the Voyager team. One of my professors in grad school was also on the Voyager imaging team. Her job was to predict the position of features on Jupiter so they'd know where to point the cameras on, off of Voyager to get what they needed. So this is a Voyager 1 status talk. So what's going on? Well, they're having a communications problem. In November 2023, just a few months ago, telemetry from the spacecraft became just a repeating pattern of ones and zeros with no information content. For those of you who aren't familiar with spacecraft telemetry, it's a very organized, telemetry is usually a very organized sequence of ones and zeros, and it's usually packaged in things called packets. Think of a packet as like a page in a book. And to signify the start of a packet, there's a very special sequence of ones and zeros that the program defines, of the mission defines, so that they know, hey, this is what I know to look for to see the beginning of a packet. And if you lose those particular sequences of ones and zeros, you can no longer decipher your telemetry because you don't know where you're at, what packet you're receiving, or anything else. So the fact that they in particular lost those sequences of bits tells you that they could not decipher the telemetry. So as a result, of course, there was no science or engineering information being received. Initial analysis by engineers at Jet Propulsion Laboratory showed that the problem was in the flight data subsystem, or flight data system, which is one of 3 computers on board the spacecraft. They had actually originally thought it was a different system called the telemetry modulation unit, but they quickly determined that that wasn't the case. I don't know the details of how they made that determination. So they sent commands to the spacecraft to reset that computer, hoping that would clear up the problem, but it didn't. The problem remained afterwards. So they had to continue investigating, and they had several challenges, one of which is the hardware is very old. It was launched in 1977. So you're talking probably late 60s or very early 1970s technology. Okay, so the hardware is very old, so it's not the kind of thing you go to the computer store and purchase anymore. The documentation they have on the system is not even in digital form yet, so they're really having to look at books and reports and things like that and read through them because they can't even do searches. Okay, they have to look at them by eye. furthermore, the people who designed and built the system are pretty much no longer alive. So the people who really knew the system the best aren't available to consult to find out what they might be able to do or how to investigate. And finally, the one-way light travel time to the spacecraft is 22.5 hours. So it takes nearly 2 days to send a command and then know if it worked. So those are some really serious investigative challenges that the team is having to deal with. Next. So what they've been doing is on March 1st, they commanded the flight data system to skip around and use some different pieces of the software, hoping that maybe they could avoid the problem area. And so on March 3rd, they received the data, okay, 2 days. And they looked different. The data they received looked different from the unreadable stream that they had been receiving. Excuse me. And on March 10th, they determined that the data was actually a memory dump of the flight data system. They got code, data, and science and engineering data, basically everything that was in the memory of the computer. And you need to also understand that missions often, or if not always, include capabilities to do memory dumps and of their computers, and that gives them a way to determine whether or not there's been some corruption in the memory. And so anytime they do a software update, they load their flight computer and then they immediately dump the flight computer so they know what they actually loaded, what was actually received by the spacecraft, so that if they start having problems, they know they know what the system is supposed to look like. So this memory dump will allow the engineers to determine if the code is corrupted or if the data has been corrupted. Okay, because they don't even know where the problem is. And as a result of having this memory dump, there's hope that the cause of the bad telemetry stream can be identified and perhaps corrected. Next. And so the conclusions are is that the Voyager 1 communications issue continues as of this moment, as far as I know. The engineers have the memory dump from the flight data system to examine, and by comparing with what they had expected it to be, they can hopefully identify the origin of the problem. And so there is hope that the problem can be corrected and Voyager 1 will be able to continue transmitting data about the interstellar environment. Okay, it's one of two spacecraft currently in the interstellar environment, the other one being Voyager 2. So losing one of them will be a big loss for our understanding and observations of the interstellar environment. And just for information, those are some websites that I used in looking at this. And that's all I have.
Thanks, Wayne. That's really, really amazing. I'm glad I'm not working on that problem. And it's nuclear power. Is it have power to spare for a while?
Yes, it does have nuclear. It's got RTGs, so they do have plenty of data or plenty of power, excuse me, to keep operating at least for a few more years. The power level is decreasing as the plutonium decays, but they do still have the power. It's worthwhile trying to figure this out.
Yeah, cool. Thank you. Anybody else have questions for? Yeah, we got another question.
He said something about an RPG or something. I couldn't hear it.
What was that other power source?
RTG, a radio isotope thermoelectric generator. It's basically a bunch of plutonium that decays, creates heat, and then thermocouples convert that heat into electricity.
Hey, Wayne, off the top of your head, do you know for New Horizons, which, is winging its way out to interstellar space, are there plans to leverage that? Is that going to continue to send back data like the Voyagers?
I believe so, but I don't have the specifics off the top of my head. But yeah, it is headed toward interstellar space and it will be there eventually. And I believe it's a power source. It's also nuclear.
Yeah.
Is actually a better power source because it's several generations of power sources later. So it should last a good long time.
And one interesting thing on that, on New Horizons, is it was built so long ago, the main chip in that is a Sony PlayStation 1 chip. because at the time it was the most sophisticated chip that was made, and it was proven robust, and they knew they couldn't do a service call, so they went with that.
Cool. So you can play Fortnite if you're out in the space.
At least Pong.
Well, just so you know, Hubble's big computer is a 486.
Wow. Wow. Yeah, we can only imagine what's on Voyager 1. It's a 8-bit something or other with, and I think Steve Priebit put in the thing, it's probably, all that code dump is probably assembly language. Anyways.
Yeah, almost certainly.
So let's, we don't have much time, so let's take a quick look. Are you on, Steve?
Yes, I am.
You want to talk to this? This is really cool.
Yeah, this was the solar eclipse in 1970. A couple of us grad students at UVA went down a little ways into Virginia and found a spot. It was a beautifully clear day. I had an 8mm, or I guess maybe a super 8mm movie camera, which is what I use to take these pictures. And these are just frames from the movie camera. Of course, no way to tell whether it was focused properly or exposures were right. But it was a fantastic sight. We saw the shadow of the moon coming across the field towards us. We saw the shadow bands. And if you go to see the total solar eclipse this time, don't get so wrapped up in trying to take pictures and things like that that you miss all the things that are going on around you. It's pretty exciting. Then in 2017, I was on a cruise in Alaska, so I didn't see the total eclipse, but the cruise ship produced cookies with the partially eclipsed sun. And you can see my my friend there is holding up one of those cookies that they passed out on deck while people were up watching the eclipse in Alaska.
Nice.
And then on the right, as I think everybody knows, the weather has been pretty atrocious for quite a while, and because of some personal problems, I've only had one chance to get Pons Brooks. But I did get it the other night with the 14-inch with Hyperstar, and it's it's pretty low in the sky, and evening twilight is still going on, so it's kind of tricky. But I thought this came out pretty well. This is a 2-second exposure,
Nice.
and it's a stack of 10 frames.
Nice. So you were aligned and ready to go from the day before or something?
What's that?
Where's your telescope aligned and in hibernate mode? Like
Yes, my telescope's in a dome. It's an equatorial. It's on hibernate mode. I just turn it on and I'm ready to go.
Nice.
Oh yeah, yeah.
Thanks.
Yeah. But on all the frames I took, over a third of them had trails in them from satellites.
Oh yeah, sure. You gotta remove that with software.
Yeah.
Joel?
Yes.
Joel?
Oh, I forgot that I sent this. I forgot that I sent this to you.
Yeah. It's really,
Yes. From
about
18. Yeah, that was my first last lunation at new moon. So this was. Is there a date on the bottom of that?
I can't see it if it is.
Yeah, I can. But this is the Eta Carina Nebula from my balcony with the sea star covering up the landscape lighting with towels. And this was, you can see 100 minutes. And at that time, I didn't it was like one of the first weeks with the sea star. So I was not saving the individual fits. So this is just what the sea star did. And then in my iPad was adjust the black point and increase saturation a little bit. Bingo, done.
Cool.
So I'm pretty happy with this new little gadget.
That's about as low as you can go, even from down there.
And exactly, and it was only this was about 8 to 10 degrees above the horizon for the entire 100 minutes.
Yeah, it's amazing. Steve, are you on more Sea Star? All right, I'm gonna move on because we have a few more.
Yes, I'm here. I'm sorry. I was trying to unmute myself.
So it looks like you're getting you're having some fun with the Sea Star.
Oh man, yes. As you say, I just started imaging, and this the first thing I did in the daytime was the sun, like the week I got it. This is the sun at 4 by, the next picture. And I did the moon a night, I think a week later. And this is about the second or third time I've done the M42. But this picture I took at the public star party Saturday, and this is the best that I have done yet. And I can't wait for this meeting to be over because it looks very good outside tonight, the skies, because we're getting ready to get rain and snow Friday and Saturday. So I'm going out there for a couple of hours to see if I can point at something else to see what happens.
Great, enjoy.
All right, and thanks for showing. I appreciate it.
Yeah,
Thank you.
great, it's great. And then we have Travis. Are you on, Travis? This is just gorgeous. It's you can't tell because it's pretty. I think he has a 14-inch, but this is the Seagull. A zoom in of part of the Seagull Nebula, and I think he took some nice artistic, as he did the last time, some nice artistic license with the colors. And we have Ian. Oh, wait a minute. Ian is here with us live. Yay. Ian, sorry.
This is from West Virginia. I have an 11-inch Schmidt Caroglanian, and I use a reducer to decrease the focal length a little. And this is the first time I dabbled in calibration frames, which obviously you need to do.
Yeah. Well, that's only 30. I mean, I say only 37 minutes. That's pretty good. Yeah. Nice. It's at F6, 7 or something.
It's an F10, but reduced to about F7.
Yeah. Awesome. And then you had a couple other ones.
Yeah, Messier 95, same focal length, and then the other one is the Planetary Nebula, the Owl Nebula Messier 97.
All right, cool. And then we have one of the most amazing examples of image stretching I've ever seen with Jim Johnson.
This is M42. That's a full frame, full 35 millimeter frame, minus minor cropping for stacking artifacts. Two amazing things about this. Was taking that winter star party in Florida. The winds on that night while I was taking this image. But let me back up just a little bit. The scope is 4-inch APO refractor with 540 millimeters of focal length, and what else? About an hour and 50 minutes of exposure. Full 35 millimeter frame minus the cropping of the stacking artifacts. The wind was howling at about 20 miles an hour while I was taking this image. That's the first amazing thing to me. The second is all the detail that I was able to pick up around the nebula. And there's a new stretching tool that is a third-party process and PixInsight called Generalized Hyperbolic Stretch that I did that with. And this is the only image I've really worked on with that. I look forward to doing more.
I hope that you can give us all I've used GHS, and this is just phenomenal. I hope you can give us a tutorial on how you used it.
You go ahead.
And then we have Ken. Ken is here with some other a couple more amazing photos.
It's the Pencil Nebula. Obviously, it's a remnant of the Viola supernova remnant. It's a little tiny piece of it. And I took this from Florida.
And yet it was still pretty low in the sky, right?
Yeah, I only got about 2 hours worth of data. It was never above 15 degrees. Wow. So it was pretty happy and windy. I don't know why it's so windy in Florida lately, but apparently.
Was this at the Winter Star Party or a different?
No, this was just last month. I took my William Optics scope down. It was the first time I flew with it. And it worked pretty well, except there was a lot of heavy stuff to trips around airports with, and TSA wasn't happy with it. And this is, I took them from Florida to the Dolphin Head Nebula. The star in the center is a Wolf-Rayet star, and it's at the end of its life, so it shed its outer layers. Now it's a really hot center star that may become a supernova someday, depending on its mass.
Yeah, you need to give us some tutorial on your processing stuff too. It's so three-dimensional. I don't know. And I think you must be doing something magical in Photoshop with layers or something.
I don't think so. It's
Yeah,
usually
that's just so
the thing
cool.
everybody else does.
It just pops and comes right out.
That's amazing. Yeah.
It's just gorgeous. Well, that's all I had for photos, and we are right at 9 o'clock. So I think in this case, I'm gonna stop sharing, stop recording the meeting. And I want to say thank you to everybody for coming out. We had about 50 people online for a good fraction of the talk.